Okay, calculus students, this is section 4.5 and we're working on day 2. Yesterday we introduced the topic of U substitution and we did some relatively straightforward U substitution integration problems. So today we're going to step it up a notch and maybe work with a few radicals or where you'll see rational exponents. Got a couple of those coming our way, and then we're going to look at trig integrations. So those are the two topics for today, and I may not do all the examples, but we'll get a good amount done. So once again on this one, we're looking for the expression with the higher degree, and just comparing the two, I notice I've got a 5th degree versus a 4th degree. So I'm thinking that, over here with the x to the 5th is probably a good selection for the u. The other thing that makes it an even better option is the fact that it is a composite function. My outer function is the 1/3 power. My inner function is this expression of 4x to the 5th plus 5. So my best guess is that I should let u equal 4x to the 5th plus 5. By doing that, I can come over to the side and just do a little planning out on my scrap paper here, and thinking u should be equal to this. If I were to take the derivative of each side, I'd have du with respect to x of 20x to the 4th, and that's all I get there, right? So now I kind of come back across and I look over here at my original problem. If this becomes my u, I'll have u to the 1/3. Then I have to find a way to take care of the rest of the problem. And obviously, an 80 and a 20 are not exactly the same. However, if I simply multiply both sides by 4, I can easily, let's put it up here, I can easily turn that 20 into an 80. So I'm going to have 4 du equals 80x to the 4th, and then I'm going to multiply both sides by dx to bring it up over there. All right, so now we want to rewrite our integral using these u's and du's. So like we talked about, this 4x to the 5th is going to get substituted in with a u, or replaced with a u. So I have u to the 1/3, that outer function being 1/3, and 80x to the 4th dx is equivalent to a 4 du. And I can put my 4 out front and mark the du down. Now when I see everything with the same variables, I may proceed. So we just have to actually integrate the problem now. So I've got the 4 outside as a multiplier. U will get raised to the 1/3 plus 3/3, which creates 4/3 for us. So I'm going to put a 4/3 power. I would divide by 4/3, but dividing by 4/3 is the same as multiplying by 3/4. Dividing by a fraction is like multiplying by its reciprocal. So I end up with 4 times this stuff. Now, 4 over 4 is division, and that becomes 1. So I get an answer of 3u to the 4/3 plus c. And the final step in this process is, let's bring it back to x's. So I look back on my chart and I notice that u should be replaced with 4x to the 5th plus 5. That was raised to the 4/3. Add c. And that becomes the antiderivative for our problem. Number 8 is looking just a little bit different. I noticed the radical sign, and I know, well, I could rewrite this as 48x squared 4x cubed plus 1 raised to the 1/2 power dx. And now it becomes a problem very similar to the one that we just finished up. I'm looking for higher power, so I'm comparing 2 and 3. Well, obviously this is a little bit an expression with a higher degree. The other thing about this one that makes it a very prime candidate is the fact that it is a composite function. My inner function, outer function exists there. So my suggestion is, let's let u equal 4x to the 3rd plus 1. And then derivative of u with respect to x would be a 12x squared. And I have 12. Over here I see 48x squared. Well, that's easy to solve, isn't it? We'll simply multiply both sides by a 4. And when I multiply by 4, that's going to give me 4 du is equal to 48x squared. Multiply up, bring that dx over, so we have a complete substitution for 48x squared dx. All right, let's go through our process of rewriting in terms of u. So this here becomes u. It is raised to the 1/2 power. The 48x squared dx gets substituted over here with the equivalent 4 du. Since 4 is a multiplier, I'm going to pull it out front. Now it's simply integration step. So I'm going to integrate u to the 1/2 by adding a power. So add 2 over 2 to the 1/2 and I get 3/2. I divide by 3/2, but dividing by a fraction, we know, is like multiplying by its reciprocal. So I'm just going to rewrite and multiply by that reciprocal. This is like a 4 over 1, so when I multiply fractions, multiplying, I go across the top, I multiply the denominators, I get 8 over 3. The u, we can swing back into our x terms, so I get 4x cubed plus 1 to the 3/2 power and plus c. Not so bad. So here are the trig ones. A little bit of trig practice. I think I have 3 or 4 of these. This trig one here, sine, if I just had the integral of sine, hey, we could have any variable we wanted. Let's say we had sine u du. Well, the integral of sine is simply negative cosine of u, isn't it? Plus c. That's kind of the ones we're used to. They were pretty easy for us. But what makes this particular problem a little bit more difficult is the fact that it's not just a nice simple little 1x. Say this had been 1x. That's much easier to deal with than 20x. Although you're going to find working 20x isn't that much more difficult. So my suggestion is, let's let u equal this, because then we can get this into some sort of sine of u, and then hopefully dx will switch out with du. So upon my suggestion, let's just try 20x. And then the derivative of u with respect to x will look like a 20x. Or I'm sorry, just 20, right? Derivative of 20x comes down to 20. I don't really need 20. All I need is a single 1. So first off, let's swing our dx, multiply it up and over so that we get the dx in a numerator. And now we said we really only want one of them, so let's divide both sides by 20. That's fair. As long as you do to one side what you do the other, you haven't broken any equality properties. So this will divide and give us 1. So I get 1/20 du is equal to a dx. There's our substitution. All right, so we were talking about how we would love to get this into sine u, and now for the dx, I have to trade this dx out, and dx, it says, is equivalent to 1/20 du. And that 1/20, since it's a multiplier, we can bring it out front. We're left with that. 1/20 just keeps riding along since it's multiplying. And the sine of u integrated becomes negative cosine of u plus c. That negative, I'm going to bring it out front so nobody thinks I'm doing a subtraction problem there. And, oh, instead of u there, let's just replace it right now. Save ourselves a line of writing, and we get cosine 20x plus c. What's the purpose of this u sub? Well, the purpose is it provides a very, I guess, systematic way of coming up with the integral. Now, after you've done a few of these problems and you have something like this, you can probably realize that, hey, it's going to end up being the reciprocal of whatever's in front of my x. And we see that, 20 came down to 1/20th. The negative came from the fact that we were integrating a sign, but sometimes they're pretty easy to pick up patterns and you're able to do it a little bit quicker than writing all the u subs down. This one just got a little bit more crazy. Last time we didn't have anything multiplying by our sine or cosine here, but the 3x seems to make it look a little even more complicated. I'm going to let u equal this. This is my gut feel. I notice that this power is this is a degree 2, whereas this is a degree 1. So if I have a term that has exactly 1 degree higher than the other term, that's a good thing, because what happens when I do derivatives? Well, when we do derivatives, we get this reducing by 1 power, don't we? We subtract 1 in that process. And that is going to be nice then, since I had an x in the problem. This is perfect for our u substitution. All right, and I kind of did the process over here. I took the derivative, brought my dx up over. I've got 6x dx that I want to come out with. Instead of 6 of them, I only need 3 of them. Well, that calls for division then. Let's divide by 2. Or you could say I'm multiplying by half. That would be fair, wouldn't it? 1/2 du is equal to 3x dx. Perfect. I'm kind of done with my u substitution systematic block over there. So now I can get down to business and replace things. So the 3x dx is equivalent to a 1/2 du. You didn't see it, but my eyes actually looked down there at what was going on my bottom line to see what was the equivalence. So 3x dx is a 1/2 du. And cosine we don't need to change, but the inside part of cosine, now look over at your thing and you're going to see, oh, it's u equals 3x squared, so that becomes my u. Let's see, integrating cosine. Oh, well, that is a sine, isn't it? That'll just become sine of u plus c. And I'd have a 1/2 sine, replace our u. Once again, look over to your box. It's so handy because all the things you need to reference are right off to your right. And we get 1/2 sine 3x squared. Very nice. Oh, they just keep getting harder, don't they? So this one looks a mess. And, when we did this in class, one of the kids said, well, okay, the first thing I noticed is I've got a cubic and a squaring. So probably I should choose the thing cubed. And when we're working with expressions like x squareds and x cubes and things like that, that's a really good rule to follow. When you're working with trig functions, there can be a little bit more to it than just that. And on this one, I want you to think about tan of just x. What is its derivative? Versus secant. What is secant of x derivative? Well, tangent, its derivative is secant squared x. And secant, its derivative is secant x times tangent of x. So which one do I want to use? Which should I let be my u? Well, because tangent's derivative yields secant squared, if I replace this with a u and have like u cubed, so I'm replacing tan x with u, that gives me u cubed. Notice that I get a secant squared dx left alone, which is going to be this right here, isn't it? Secant squared. So you got to do a little bit of forward thinking. Otherwise, just, guess what your u should be. Try it out, run it through the paces, see if it works. If it doesn't, select something else. No harm done. All right, we're taking our best guess. We're saying, hey, I think things are going to pan out nicely if I set u equal to tangent x. Let's take the derivative of both sides. So du is equal to a secant squared x, and this would have been divided by dx. Instead of putting it there, I'm just going to multiply right away and bring it up and over. And now that is a perfect, perfect, perfect substitution for secant squared dx. So we're going to have tangent x cubed is going to be replaced with a u cubed, and secant squared x dx gets just du. Whoa, look how simple this just got. We have been integrating u cubed for quite some time now, or something raised to the third. We know how to integrate this. Add a power gets us to a fourth, and then I divide by 4. Pick up my c, and I'm almost done. The hard work is done. Now it's just replacing and getting it in pretty picture here. So you can't see my eyes, but my ahs are going up there, and I see that u was originally set up to be equal to tangent x plus c. That's one way of writing it. Some of you maybe would prefer to bring that fourth power of tangent in between tan and the x, which is fine. Either presentation is great. And now let's say we had multiplication, why not have division, right? Let's create a quotient. This is still kind of the same thing. It's not really based on cubes and squarings. It's more so some of the tricks of the trade. You look for those degrees for just like expressions, polynomial type expressions. When I get into trig functions, I think of the trig function as well as its derivative. And if I have its direct derivative, then I want that item as my u, and then its derivative is going to fall in place. The other thing that can be true is when an object sits in the denominator, you often want to allow that denominator to be replaced with u. So just off of a hunch here, I'm thinking my cotangent should be my u because it's sitting in the denominator. And, you know, that gut instinct usually fares out pretty well. And another reason is when I take the derivative of cotan, I'm just simplifying it here. When I take the derivative of cotan, do you remember what it is? It would be negative cosecant squared. And the thing that I notice is the numerator is cosecant squared. So this is looking really, really, really good. Let's proceed with letting u equal the denominator. U is equal to a cotangent of, I've got to have that 4x. I can't simply replace that with something else. So I'm going to go cotan 4x, take the derivative of each side with respect to x. Derivative of cotan is a negative cosecant squared of the inside 4x. And then when I take this derivative, that was the derivative of just cotan. Now we also have to do the chain rule, which gets us an additional 4 there. So the derivative of 4x becomes 4. So my du is going to equal negative 4 cosecant squared of 4x. And I'm not going to write the dx down there. I'm going to swing it up and over. All right, so now I got to come back across and just check to see how close I matched. I see the cosecant squared for x dx. So I've got part of it, and the number portion here over on this side I'm not too worried about, because the number portion of negative 4, I can get rid of that in a real easy step just by dividing by negative 4, correct? If I divide by negative 4, it'll cancel on my right side, and I'm going to have negative 1/4 du is equal to a cosecant squared for x, dx. And now we may go back over to our problem and start putting things in place. So we said this cotan for x is getting replaced with u, so it will be a u to the third power. Ooh, I just put that kind of up too high. I'm going to bring it down a u to the third. The top stuff is right there, cosecant squared 4x dx is going to get replaced with a negative 1/4, might as well put it out front, and then du. Okay, when we did these in earlier chapter 4, and we had just nice simple things with like a u cubed underneath, we often wrote it as a u to the negative 3. So that will be easy to integrate. We add a power. Now, the number one mistake people make when they add one, they end up saying it's negative 4, but it really isn't, is it? It really is negative 2, and then I would divide by negative 2. So a negative 3 plus 1 is negative 2, and then I add on my c. You know, sometimes going to college, all professors really want you to be able to do is to be able to do algebra really, really well. Because if you know good fundamental algebra skills, you can be taught any upper level math. So what I'm asking here is, how does this simplify? What is this division by negative 1 or negative 2? Well, that's really like a fraction, isn't it? That's really like a multiplication of negative 1/2. And this u to the negative 2, well, that's like 1 over u squared. And then I have my plus c. When I'm dealing with fractions, I multiply their denominators, and I can multiply their numerators. And then I have this u squared that can go down underneath, because I could just keep multiplying all the way across. I could multiply all across the top. So I get 1 over 8u squared plus c. And now turn that u back into x's, and I can't quite see what our original u was. Oh, it was a cotangent. Oh, cotangent, let's see, it's going to be underneath, hello, cotangent squared of, my brain is going, it's been a long day, 4x plus c. And that is the solution to our problem. So you have a little bit of homework. It's out of the textbook. Right there it is. If you want to jot those down and look in your textbook to do them, that'd be great. I'll see you in the next class.